Hello everyone, Assalamu alaikum. Welcome back. In this video, I want to talk a little bit about making scientific computing a little bit more efficient using a concept called vectorization in Python. So why am I talking about this right now? The reason is because in the next video, I want to show you an implementation of perceptron in Python using NumPy and PyTorch. And I will make use of this concept of vectorization in the next video and the videos later on as well. So here I just want to give you some background information on that. Now in general, running computations is a big part of deep learning. So deep learning is a very applied field. Most of the things we do here requires large amounts of computations. Some of you may wonder, why do we use Python then? Because Python is not known for being a fast language. I mean, the truth is, usually Python is not really a big bottleneck in deep learning because we use efficient libraries like NumPy for CPU computations and PyTorch, for example, for GPU computations, which implement algorithms very efficiently in underlying C++ routines and CUDA routines. And so if you would like to take out Python or take Python out of the equation and just look at these implementation, let's say in C++ and everything, Python would only slow things down by 10% approximately, and that is what is estimated by the PyTorch developers. So whether you use PyTorch, Python or not for writing code, it does not really slow things down because Python is only like a glue around these lower level libraries. So it's basically just a wrapper around things. It's not that slow actually to use PyTorch in Python compared to, let's say, other languages. However, that only applies if you use Python smartly, because there are certain things that are not very fast in Python. Let's just talk about vectorization, and now maybe stop the video at this point and take a look at what is shown here, and then try to answer the question, what are we computing here? It is the net input, the weighted sum from the perceptron. So here I'm just defining the variables. I'm using this notation where we have bias implicitly as a weight. So instead of bias, I could also have written W0. It would have been maybe a little bit more clear, but I think you know what's going on here. What we have is the inputs x0, x1 and x2. So I'm just using some arbitrary values here. Same for the weights. So in the bias, these are the parameters that we want to learn. Usually here it's just about computing the net input, no learning involved. So I'm assigning them to a Python list here. These are now Python lists, and then in the bottom area here, this is how we compute the net input. So z is our net input. What's going on here is we initialize z to 0, and then in the for loop we iterate over the indices I to length of x or m. So from I to m, where length of x is equal to m, which is the number of features. And for each iteration, we update z. So this is how we compute the weighted synthesis equation. Weighted synthesis equivalent to this one that we computed before as well, if you remember. And there's not that much more to say about that. This is just that using a for loop to compute the net input. Slightly modified version of this would be using a list comprehension, and actually this is even a little bit better than a list comprehension in that way, in that context, because we don't have to construct the list. So you could actually put square brackets around this. It's not necessary. If you don't use square brackets in Python, it will be a generator expression with a square brackets. It will be a list comprehension. Either way, both are slightly better versions of that for loop, or that's at least what the local Python developer would tell you. Here it's everything on one line. You have something like the multiplication for xi and wi, and then in the zip. So here zip is iterating over two lists at the same time. In that way, I mean, it's the same thing, it's just a little bit more compact. I would say compact is nice if you care about the number of lines of code, sometimes a little bit harder to read. But anyways, you should be familiar with both ways for writing things, because they are very common in Python ecosystem. Now there is another way. I recall the dot product that we talked about, x, the vector x dot w. So that would be another way of computing our net input. This is what I'm showing you here at the bottom. So I'm actually using NumPy now. I'm using NumPy arrays. Like I'm converting the lists to NumPy arrays. NumPy arrays have efficiency benefits compared to regular lists, because in regular lists everything is a pointer to some random location in memory. So if every time you want to look something up, Python has to find or go to the location in the memory. All these these are like random locations in NumPy arrays. Everything is so it's basically a fixed size array. You can't make array bigger compared to a Python list, but in that way everything has a fixed size. You only need to store the first location of that array in memory, and then Pi or the computer can use, for example, the CPU caches like the L1 and L2 cache to do certain computations more efficiently by pulling out numbers from memory more efficiently. So NumPy arrays for computing much faster than Python lists. And also you have linear algebra operations already implemented for it, like the dot product, for example here. So here I'm computing the dot product between x transpose and w. So that's how we compute the dot product. You can actually also write x back dot t. So if I do this, dot w back should be the same. Also one thing is that here is that in this case our NumPy array only has one dimension, so you don't actually have to do the transpose. And for the rest of the videos we will also assume that you have some familiarity with NumPy. PyTorch will be very similar to NumPy, as you will see shortly. Okay, so you can just confirm these are the same computations, or mean different computations but the same results. Now here are all the three options for computing the net input listed. So my question to you now is, for large vectors, which one is the fastest? So you have guess how fast these implementations are, and then on the next slide I will show you the results. And you're also very welcome to try this on your computer, for example. So the results are as follows. I was using the time it magic function in Python because I find it personally very convenient. So here with -r you set the number of repetitions, and this is the number of loops. So it's running the computation 10 times as one experiment, and then it's repeating this experiment 100 times and averages over those. So you can see it computes the mean and standard deviation of that, because sometimes depending on what your CPU is currently running in the background, it may be faster or slower. So in this way you get some better more stable estimate by averaging over multiple experiments or repetitions. So the first case, the for loop here runs in like 40 milliseconds approximately. The list comprehension or generator in that case is a little bit faster. It's 30 milliseconds, so it's 10 milliseconds faster. It's quite a bit. I mean, it's like, I would say, almost 20% or something. But what's really interesting is the vectorized implementation. Now instead of having, let's say, 40 milliseconds, you're almost down to 40 microseconds, where micro is 1000 times faster than milli. So in that way there's a huge improvement by just using NumPy code here. So this vectorized implementation, and this is why in deep learning we want to avoid to use for loops. So wherever you can, if you ever see a for loop in your code, try to eliminate that by using dot products or matrix multiplications in NumPy and PyTorch. Now regarding the reason why they are more efficient, we haven't really talked about why it is more efficient. If I go back a little bit, so if you look at the for loop here, what is going on here is that things are computed in a sequential order, right? So the for loop is doing one thing at a time. It's doing this computation for the first index, and then it goes back and does for the second, and so forth. So it's doing this sequentially, one at a time. However, for dot product, for example, you can think and compute things in parallel. So of course you have to have the results of that when you want to add that up basically, but each pair can be computed in parallel, right? So you can already carry out all multiplications at the same time. You don't have to wait until one is finished, so you can compute things in parallel, and in this way we can leverage parallel computing. There's something called SIMD, sorry, SIMD. It's a similar operation but on the same data. So that is one advantage why GPUs are kind of especially good at this, because GPUs have a lot of scores. So you can actually carry out large vector data products or large matrix multiplication very efficiently. So in matrix multiplication you have multiple dot products at the same time, and you can parallelize the dot product computations. And going back to the question I raised earlier, why the human brain is, for example, so much more powerful than a neural network, one reason could also be that it's just also the number of connections. So the brain may not have that many parameters as like these big language models, but it has a lot of connections. Although it's also not really true for language models anymore, because transformers also have these attention layers which have an attention over all the inputs and stuff like that. But let's consider here a GPU for reference. The GPU has a lot of transistors. It has 21 billion transistors. You can see this particular one from 2017, whereas the brain has 16 billion neurons. So a GPU actually has more transistors than a brain has neurons. So one idea why the brain is also so much more powerful than a GPU, for example, is that um, there are just so many connections per neuron compared to the transistor. So transistor only has approximately 10 connections on average, whereas the human brain has about 10 to 100,000 connections per neuron. So in total you have like 10,000 billion connections in the human brain. All right, so but going on, moving on, this was like a short interlude into the vectorization.